involving e and the natural log, and then we're going to use a new interest formula for interest compounded continuously. So the abbreviation that we use for this one is PERT, P times e to the RT. So first of all, figuring out where e comes from. So the definition of e is the limiting value of a equals 1 plus 1 over n to the nth power. Hopefully this looks kind of familiar. Our compound interest formula is pretty similar. So P, our principal, is $1, our rate is 100%, and our time is 1 year, and that's how we get the value of E. What it means by the limiting value of E is that as n gets really large, you're going to get pretty much the same value. So if you take this formula right here and substitute 100,000 for n, and then you substitute 1,000,000 for n, your answers aren't going to be very much different, and they'll both be pretty close to about 2.718. So that's where we get our E value from. And then, so this little note, remembering that n is the number of times each year the interest is compounded, as that approaches infinity, as n gets really, really large, we call it compounded continuously. So then it kind of morphs into this formula that we have down here in green, the continuous interest formula, P times e to the RT. The natural log of x is the inverse of e, or log base e of x. And then we're also going to use the half-life formula down at the bottom here. So n of t is the amount remaining, n sub 0 is the initial amount, k is the decay constant, and then t is time. So first we're going to take a look at a few properties that we're familiar with and show how it works with e in the natural log. So our first property is b to the log base b of x, meaning the b and the log base b cancel each other out. So for our new property, we have e to the natural log of x power, and the e and the natural log cancel. So those are inverses of each other. Don't feel like you have to copy this chart down if all of these properties make sense. We're just using them with a different base E instead of base B. So our second one is similar to the first one, and then the last two are the properties where, for example, b to the 0 power equals 1. Well, similarly, e, remember natural log of base E, to the 0 power equals 1 as well. And then anything to the first power equals itself. Well, over here, e to the first power equals itself as well. So we're going to use those inverse properties. E to the natural log cancel, leaving us with 6 plus x. Our second one, the natural log of e, cancels, leaving us with 2 over x. On c, there's a 4 in the way. The e and the natural log aren't right next to each other, so we have to raise 4 as a power so that we get e to the natural log of 2 to the 4th. Then we can cancel our e and the natural log. 2 to the 4th equals 16. All right, so now we're going to take a look at the PERT formula, interest compounded continuously. So this is the key word that you want to look for when you're determining whether you use PERT or whether you use the other interest formula that we looked at. So if it's compounded continuously, that's PERT. So we'll substitute what we know. We invested $2,500. Our rate is 0.02375, and we're investing for 10 years. So when you substitute this in your calculator, when you evaluate this in your calculator, make sure some calculators automatically come up with parentheses when you push your E button. Mine doesn't, so I have to put a parenthesis there and then close it to make sure it knows to multiply before it takes e to that power. So for this one, I got about $3,170.19. Next example, we're looking at how long it would take for an investment to triple. The problem with this question is we aren't told what our initial investment is. So again, I noticed my keyword compounded continuously, so I'm using my PERT formula. So let's just make something up and see what happens. Let's say we invested $100. Okay, so if $100 is our initial investment and our interest rate is 6%, to triple it would be $300. So the first thing we're going to do to solve this is divide both sides by 100 and we get 3. So anytime you're given a question like this, if you're asked to triple, you'll substitute 3. If you're asked to double, you'll substitute 2. Whatever value you're given in the equation will be the value that lands right here after you divide both sides by your initial investment. You want it to triple, so you can start your equation right here. So then to finish up, to cancel the e, we'll take the natural log of both sides. And to solve for t, we'll divide both sides by our interest rate. And I got about 18.31 years. Last example, we're going to take a look at that decay formula. So if you remember, the decay formula was n of t equals initial amount times e to the negative kt, where k is the decay constant. The decay constant changes for each, we're usually talking about radioactive materials when we're using half-life. And the decay constant is different for different material. So we have to first find the decay constant. Again, we're thinking, well, I don't know how much I started with. But again, it's half-life. So what that means is similar to that last example where we wanted our investment to triple. So after we divided by the initial amount, we were left with 3. Well, now we're looking at half-life. So after 24,000 years, half of what we started with will be left. It doesn't matter what we started with, half of it will be left. So thinking about dividing by our initial amount, we get half equals e to the negative kt. Well, the time in this case is 24,000 years. That's how long it takes for half the material to decay. So we substitute 24,000 in for t. To cancel the e, we'll take the natural log of both sides. And I'm going to rearrange this so that it looks more like a coefficient. And I am missing a 0. So to solve for k, we'll divide both sides by negative 24,000. And I got about 0.00029 is our decay constant. So then for the last part, we are going to use that decay constant to figure out how long it takes for a 1 gram sample to decay to 1/10 of a gram. So 1/10 of a gram is the amount remaining. If I substitute 1 for initial amount, it doesn't matter, I'm multiplying by 1. So there's my decay constant that I just found in part A, and we're looking for time. So again, to cancel that e, I'm going to take the natural log of both sides. And then to solve for t, we'll divide both sides by our decay constant. And in this case, our answer is 79,726.27 years.